All right. Thank you everyone for tuning in to today's Origin seminar. Before we introduce the speaker, I just want to remind everyone to please keep yourself muted during the talk. If you have a clarification question during the talk, you can put it into the chat and one of the organizers will ask the speaker. Otherwise, please hold your questions until the end. So today's speaker is going to be introduced by Chad Bender. Chad, take it away.
So I'm really pleased that we have Lily Zhao talking to us today. Lily is a graduate student at Yale. She's just finishing up her PhD. She's been working there with Deborah Fisher on the EXPRES spectrograph, which is a precision radio velocity spectrograph that was installed a few years ago at the Discovery Channel Telescope and is now operating regularly on Sky. Lily's been very involved in the data analysis, made some critical contributions to the data pipeline, and really worked hard on trying to get the most out of the spectrograph data that's coming in. So I'm really looking forward to hear what she has to say, and yeah, I'd say take it away.
Thanks, Chad, even though you kind of spoiled some of the slides of my talk, but they'll have pictures this time when I go over it. So yeah, like Chad said, I've been working on EXPRES, the Extreme PREcision Spectrograph, with all the great people listed here who have all contributed to this project. EXPRES is designed as a precision RV spectrograph to try and find Earth-like planets using the radial velocity method, which, as a super quick review, the radial velocity method tries to find the movement of a star as the star and the planet orbit their common center of mass. We detect this with the Doppler shifts, and so we can see the star moving away or towards us as the light either being red shifted or blue shifted, and that's the primary method for finding these planetary signals. As you are probably all aware, the first planet was actually detected using this RV technique. It was 51 PEG, and here's the data from LOD here. And historically, even though RVs were the ones to detect the first planet, we've been detecting like lower and lower mass planets throughout history up until around a limit of 1 meter per second. So 1 meter per second is really where the RV precision has stopped in recent years, even though the trend before had been going down. And unfortunately, the Earths that we're also interested in finding actually only give rise to a signal of 10 centimeters per second, which really inspired this next generation of spectrographs like EXPRES or NUIT or HPF that's trying to get below the 1 meter per second boundary to try and probe Earth mass planets. And so as an initial flex, here are the RVs from Lowell, as I showed before. And if you overplot the RVs that we have from EXPRES at 51 PEG, they look like that instead. So from Lowell, which discovered the first planet, we have an RMS of about 12 meters per second, and from EXPRES, that RMS is instead 1.5 meters per second, which I think look a lot better. But now probably a lot of you are out there thinking like, okay, Lily, sure, it's great that EXPRES can do better than a spectrograph that's older than you are, but like, is this truly extreme precision, right? It's still over 1 meter per second. And so to answer this fairly aggressive hypothetical question I've now posed to myself, I would say, no, this is definitely precision RVs, but to get to the idea of extreme precision RVs requires a lot more work than these initial 51 PEG observations we took while the instrument was still commissioning. And so with this talk, I want to go through the different levels of innovation that are required to achieve truly extreme precision radial velocity measurements. Because when we look at a star, we want to be looking at it with an instrument that's stable enough to be returning raw data that isn't varying in unknown ways. And once we have that raw data, we want a data pipeline that's high fidelity enough to return spectra that we can trust and doesn't have any mistakes from the extraction or the instrument. And then once we have that spectra, we want to make sure we're modeling the data in a way that returns RVs from just the star and the star alone, no tellurics, no stellar activity, things like that. And so with this talk, I'll go through each of these 3 stages. I'll talk about some of the things EXPRES has done to improve on each of these areas and give kind of a benchmark of how EXPRES is doing. So first up is instrument stability. EXPRES is installed at the 4.3 meter Lowell Discovery Telescope near Flagstaff, Arizona. Something we really love about this telescope is that it has this instrument cube where the TO presses a button and within seconds you've switched to a different instrument. So this means that we can get scheduled a lot of partial nights per year rather than full nights. And so we get half nights instead, or quarter nights, which allows us to be on sky up to 280 partial nights a year. And so this really gives us the high cadence and the time baseline that you need to find RV signals. As a summary, EXPRES is an echelle spectrograph, and this is a design that particularly allows for higher resolution and can separate out more spectral features. So here's kind of a cartoon diagram of what an echelle spectrograph looks like. You have an entrance slit where the light goes in. It hits a concave mirror from which the light exits in parallel, and it hits the moneymaker, this echelle grating, which is a series of prisms that then separates the light out by wavelength. It goes through a culminating lens, which lines up the wavelengths of light by their wavelength, and then goes through a prism that cross disperses the light or expands them in another direction, so the Y direction rather than the X direction, which is more commonly associated with wavelength, before hitting a detector where all the the photons are read out. So here's EXPRES in its lovely, cozy little vacuum chamber. EXPRES is environmentally stabilized in this vacuum chamber, which allows it to be passively temperature controlled. It has 3 levels of vibrational isolation. So the optical bench here, which contains all the mirrors and the prisms, is vibrationally isolated from the vacuum chamber, which is then vibrationally isolated from the floor. And the floor itself is actually vibrationally isolated from the telescope. So we poured an independent concrete slab so that when the telescope moves, the vibrations from the dome movement and things like that won't transfer to the instrument. EXPRES was designed to be a high resolution spectrograph, and so it has a resolution on average of 137,000, but varies between 115 and 150,000. And as an optical spectrograph, its wavelengths range from 390 to 700 nanometers. And we finished commissioning in about February of 2019. And so here, the optical path of EXPRES is overplotted on the optical bench itself. And you can see it has all the same components as that cartoon echelle spectrograph that I showed before. The entrance slit is here where the light gets inputted from the telescope. It bounces off of our main collimator, which causes the light to bounce off in parallel streaks, hits our echelle grating, which cost more than my childhood home, which was fun to learn, and separates it into wavelengths, after which it passes through a few more optical elements before hitting our transfer collimator, which combines the wavelengths, and through these cross dispersers the size of my head that separate it out in the Y direction, and then goes through the camera barrel where it finally hits our detector. So I'll go through some of the things that I think make EXPRES really cool. For example, the fiber mirror, the camera barrel, and also our detector. Our front-end module does actually a lot of the work for us. The front-end module goes on the telescope and guides the light from the telescope to the instrument. So it makes sure that the light from the telescope hits the spectrograph optics at the same place in the same way each time. So there's no variation from the light path. And it starts with this fast tip tilt mirror here, which looks at the image and makes sure that the fiber at the center of the mirror is always centered on the same part of the star. And the cool thing about this is that the fiber mirror actually had this little notch cut into it, and then we took a bare fiber and we inserted it right into the mirror face. So there's no occulting optics in the back end that could fail or move in mysterious ways to prevent this from working. But working with the bare fiber means that if you breathe on it, it will break. So it was some pretty tricky engineering, but it does have results. And you can see from this plot that without this fast tip tilt mirror, the fiber center will move all over the place, as shown in this red curve with respect to time. But with it on, you have much more stability in where your fiber is pointing, which helps us make sure that the light entering our spectrograph is as stable as possible. Once it passes through our spectrograph, we also have this camera barrel that's optimized for a uniform line spread function. And it also mitigates any additional sensitivity to how the light has been entered the spectrograph. And so this is done through a series of 8 different lenses throughout the camera barrel, because I'm pretty sure our instrument scientist, Colby Jorgensen, was using the ZMAX to see how light will go through the instrument. And there's a checkbox you can check for maintain a uniform line spread function, or like mitigate sensitivity pupil illumination, and also one for minimize the number of optical elements, and he just left that one unchecked. And so this was his pride and joy, and these 8 lenses make sure that the way that the light looks or spreads out across the detector is very uniform, and if it does change, it changes smoothly, which is very important for lines looking similar no matter where they appear on the detector. And lastly, we used what was at the time fairly new technology, an STA CCD detector. This detector is huge and was manufactured in such a way that all the pixels were laid down at one time. And so before, a big concern was that pixels would be laid down in blocks next to each other. But if there's any error in how the blocks were laid down, they might have shifted it a little bit. And then as the photons pass back and forth across these borders, the shift would be inaccurate because the pixels, which are assumed uniform, wouldn't actually be. And so instead, we opted for this large detector, which has none of these stitching errors. And we also have, so our science fiber that injects the light is shown here in green. We have an additional fiber that is basically the same, just a little bit larger. And this allows us to inject light on the edges of our science fiber. And so using this, we can still characterize the detector's behavior on the edges of our science information without having to move the science fiber too much. And this also allows us to create a master extended flat to help us with flat fielding across the detector. And in this way, we can get good information about anywhere that science information fits on the detector and then correct for it appropriately. So when you put all of that together, you get a raw image that looks like this. This is a raw image of 51 PEG taken by EXPRES, where each line is colored by the actual wavelength of that pixel. And though I mostly show this picture to flex a little bit because I think it looks really cool, it does show some of the important things that we have to consider when we're going from raw data to extracted data. For example, you can see that the data appears on these bands across the detector. This is because of those cross dispersing prisms before that separate the data in the Y direction as well as the X direction. And they're fairly independent in terms of how they're treated with by the extraction pipeline. And you'll notice that each one has a bit of a curve to it. And also the orders, the echelle orders down here are more spaced out than up in the red where they're closer together. And that also describes how the wavelength gets dispersed throughout the spectrograph. So here, the difference between one pixel to the next will be wider than over here, where one pixel to the next will have a smaller wavelength difference. And so these are all sorts of things you have to take into consideration when trying to assign the wavelength or the color of each pixel. The dark bands you see across each order are actual spectral absorption lines. You'll notice that they're very vertical and up and down, which is very important and something we put a lot of effort into creating. And this means that all of the light hitting a row of pixels will have the same wavelength. And so it won't be confused for any other neighboring wavelength, or the effects of any neighboring wavelengths. The way that we assign these wavelengths is through calibration sources. So calibration sources are sources that emit lines of known wavelength. EXPRES has both a thorium-argon lamp, which has thorium and argon line emissions, for which we know the wavelengths due to atomic physics. But we also have a laser frequency comb. The laser frequency comb gives rise to this much denser array of lines, and we know each of those lines' wavelengths from the engineering parameters of the LFC itself. And you can see here an extracted version. So if you were looking at the image above from below and looking at one of the orders individually, each of these lines is one of the white lines here, and they show up every 10 to 12 pixels, giving us incredible coverage across the detector. And each of those lines, we know the wavelength for. Another benefit of the LFC is that we can take a consecutive number of LFCs in a row and then see how much these lines shift relative to each other. And because the LFC only goes through our instrument and into the detector, we can use this as an estimate of how stable our instrument is without having to worry about the telescope or atmospheric effects or astronomical effects. And so if we do this and take a bunch of LFCs in a row, we find that the RV shift over 20 to 30 minutes is only an RMS of 3.84 centimeters per second for this data set. So it varies somewhere between 3 to 7 centimeters per second, but on average, EXPRES's instrument calibration stability is lower than 10 centimeters per second, which is great if you're trying to find a signal that is 10 centimeters per second. So that's instrument stability. Next would be the data pipeline. So how do we get from a raw image to an extracted spectra? So our extraction pipeline is based off of this Zachmeister paper. It's a flat normalized optimal extraction. And so here we have a picture of a flat. So basically just the light shine through the spectrograph and it covers in all of the orders. And then we take the same cutout from any other image we have, either an LFC or a science exposure. And we just scale the flat to the level that it needs to be to recreate the signal seen in the same cutout of the other exposure. So this brings in like inherent flat fielding and also traces, makes it less dependent on the trace positions. Another cool thing about our data extraction pipeline is that for our exposure meter is actually a chromatic exposure meter. And so when we're figuring out how many counts are hitting our spectrograph at any given time, that exposure meter itself also separates out the wavelengths of light. And this allows us to find out how much of each type wavelength of light is hitting the spectrograph over time. So this can change if you have a lot of clouds scattering the light in the atmosphere or if the air mass is changing rapidly during your exposure. And it becomes important when you're implementing the barycentric corrections, which is correcting for Earth's motion relative to the target that you're looking at. Because that correction actually changes depending on how many photons you're getting at each wavelength. And the difference can introduce an error of up to 40 centimeters per second, depending on your observing conditions. And so our big EXPRES spectrograph actually has a little baby exposure meter spectrograph sitting on top of it to contain this information. But most importantly to me, because it's what I worked on, we also implemented this novel method of wavelength calibration, which is the process of assigning a wavelength or a color to each pixel. And the way that this proceeds, it has to happen in two steps because, So first you want to find the wavelengths with respect to pixel. What that means is we have this calibration exposure for which we know the wavelengths of all of these lines that appear and where they appear. But we have to translate that information into the in-between pixels where we don't have lines. So how do we take the wavelengths of the pixels that we know and extrapolate it to all of the pixels across the detector? And then the next step, because EXPRES takes calibration exposures that bracket their science exposures, so we'll take like 2 LFCs, we'll take a bunch of science exposures, and then we'll take 2 more. How do we get the information from the LFC exposures to the science exposures that were taken in between? So how do we interpolate that information with respect to time? So 2 steps of wavelength calibration with respect to pixel, and we have to also interpolate it with respect to time. Classically, this is done with polynomials and nothing but polynomials. So here I'm presenting the data slightly differently. On the x-axis is pixel across the detector in x, and in y, instead of detector pixel as directly, I'm using absolute order instead. So the number of those bands that we saw before in the raw exposure. And so this is plotting all of the calibration lines we have for which we know the wavelength, which is the color. The sparser areas are the thorium-argon lines, and this is the area where we have that very densely sampled LFC information. And so classically, what you would do is you would fit a 2D polynomial to this information in respect to detector position and order, where y is the wavelength. And so you'd fit a 2D polynomial to interpolate what the wavelength should be with respect to pixel. And then to get it with respect to time, you would take each of the coefficients from your 2D polynomial, fit the polynomial's coefficient with respect to time to another polynomial, and then you would evaluate that polynomial at the time you cared about to recreate another 2D polynomial with respect to recreate the wavelength solution for that one exposure, which is a lot of polynomials for something that is not well described by polynomials. And so instead, I worked as an inaugural pre-doc fellow at the Center for Computational Astrophysics. I worked with David Hogg and Megan Fidel on Excalibur, which is this non-parametric hierarchical model for extremely precise wavelength calibration. So it does away with the parametric polynomial model and leverages more of the things that we now have from like next generation spectrographs. So now is the time for Excalibur, because we can move to a non-parametric framework now that we have denser line sources. This is demonstrated by this figure, which shows the line center in pixel on the x-axis and the residual of the wavelength solution. So the wavelength predicted by the wavelength solution constructed minus the signed wavelength. So for each of these LFC lines, this method predicts a wavelength for it, and it's compared to the actual assigned wavelength of it. So it's a measure of how well the wavelength solution is doing. So the LFC lines are shown as these black vertical lines, and the thorium-argon lines are the pink dots. And then if you just use the polynomial fit to the thorium-argon lines, it does as well as the blue line. If you use a polynomial fit to the LFC lines, as well as the green line. And if you use this non-parametric model instead, fit just to thorium-argon, you get this orange line as the residuals, whereas with the LFC, you get the yellow line. So you can see that when we use a non-parametric model just with the thorium-argon lines, you get pretty bad results. The orange line deviates most significantly and has the largest residuals of any of the models. And that's because it's sparsely sampled. And so you don't really have the amount of information you need to constrain the wavelength solution at all points in the detector. But if you zoom in, you'll see that the polynomial fit, regardless of whether you're using the thorium-argon or the LFCs, have essentially the same the same shape in the residuals. And so you're not really using any of the information you get out of the denser LFC lines. But using a non-parametric model, this yellow line, you get the smallest residuals of any of the models. Now is also the time to move to a hierarchical framework, which means using all of the calibration images you have to form a better picture of what the calibration state of your instrument is, rather than before when each LFC was fit independently to a single polynomial and didn't talk to any of the other LFC images. And so you can see the idea behind this in the following figure, which shows again the pixel position of the LFC line on the x-axis, but on the y-axis it's exposure number, which is kind of a hold-in for time. So this LFC was taken earlier than this LFC, so on and so forth. And so you can see that while the LFC lines do move a little bit with time, most of them form these vertical streaks and show up at essentially the same position each time. And so the LFCs taken here still have something to say about the LFC images taken there. And then, for example, this exposure, for whatever reason, with the extraction pipeline background, whatever, all of these LFC lines were missing out of this exposure. And so by treating this exposure independently, those lines in that area of information would have just been lost to us. But if you look at this figure, you can say, well, that line probably shows up around there since the lines before and after show up near there. And so in this way, you can use the entire body of calibration images you have to inform every other calibration image that you've taken. And doing this denoises the LFC information that you do have, because now you have a picture of where the LFC lines you would expect to show up given this entire body of information. And since instruments are so stabilized now with this next generation, which is required for EPRV work, this is something that will describe a lot of the calibration spaces for next generation instruments. So as a summary, before, with respect to pixel, you would fit a polynomial to your wavelengths. But now instead, we would just use a non-parametric form. So the thing that we found worked best was this piecewise cubic Hermite interpolation scheme. And this is an interpolation scheme that, while has a lot more degrees of freedom than a polynomial, still enforces monotonicity, which is something we know will be true of a wavelength solution. And with respect to time, instead of fitting yet another polynomial to your polynomial coefficients, we can instead use principal component analysis to take the entire body of calibration images, use it to find the largest axes of variation that are defined in these changing line positions, and use that to form a picture of what the calibration state of your instrument is. And so as a test of the non-parametric model, so first we did this test where we took a single LFC image, and then we took all the odd indexed lines in that image, fit a polynomial or a non-parametric model to it, and used it to guess the wavelengths of the even ones. So the odd lines independent of the even lines, predicted the even lines wavelengths, and then vice versa. We use the even lines to predict the odd lines wavelengths. And so here we have the lines plotted as typically by pixel position and order, and then colored by the difference between the predicted wavelengths and the assigned wavelengths. And so while small, you can see all of this structure there, these patches and these horizontal stripes that are showing up in this polynomial fit residuals. But if we use a non-parametric model instead, you get a much smoother set of residuals, no features, and they're all on average a lot smaller. And this is because certain things in the detector or even in our optics might propagate to unsmoothed changes in wavelength with respect to pixel across the detector. And this polynomial can't account for it because it intrinsically assumes smoothness in your wavelength solution by being a parametric fit. So using a p-chip interpolation allows the flexibility needed to deal with this very high order types of discrepancies, but it's still properly constrained by the number of LFC lines you have. And so ultimately you get less residuals. In fact, if you do something similar, but also bring in the hierarchical method, and so instead of using just the assigned wavelengths for each line, for each exposure, but instead assign the line positions using your hierarchical model, which will give you denoise line positions, you'll see that, with the polynomial model alone, the residuals for an entire set of LFC exposures is the blue histogram. Just introducing the non-parametric model gives you the yellow histogram. And then also implementing denoising by using the hierarchical component gives you the black histogram, which has the smallest spread of any of the methods. So when you put all of this together, our final extraction pipeline returns an single measurement precision of 30 centimeters per second for an SNR of 250 at a wavelength of 550 nanometers. And so here you can see the different SNR of the exposures and the single measurement precision that you return from our optimal extraction pipeline. So now that we have extracted pipeline, we also have to figure out how to model the shifts in the spectrum to return RVs that we can trust. And something I've been working on is implementing wobble, which was developed mainly by Megan Bedell at the CCA. It's a data-driven method for extracting RVs and also inferring the underlying spectral components. So the model of wobble is assuming that your observed spectrum, Y sub n, is composed of an independent stellar spectrum, Y star, a telluric spectrum, or absorption lines from the Earth's atmosphere, YT, with some added noise. The stellar spectrum is defined purely by the stellar spectrum with all the stellar absorption lines that's shifted by some RV shift. And so that's the only effect you have to be worried about, one stellar spectrum shifting back and forth. Whereas the telluric spectrum wouldn't be shifted by the RV shift since it's from the Earth's atmosphere and staying in your rest frame, but would be scaled by an air mass depending on how much of the atmosphere you're looking for. And you would also have to consider these basis vectors, which take into account how much the lines would vary based off, for example, how much water vapor or how much of another molecule is in the atmosphere as you're observing. And so wobble uses the differences between the stellar spectrum and the telluric spectrum, namely sensitivity to an RV shift versus, say, sensitivity to different air masses or water vapor, to separate out lines that either belong to the stellar template or the telluric template, and then returns RV shifts that are exclusive to the stellar template, while also giving you information about what your star and what your tellurics look like. And so, if you look at Keck data of HD 3651, you get an RMS of 3.4 meters per second. But express RVs that make use of Excalibur, of the different pipelines, and of wobble returns an RMS of instead 0.417 meters per second, which I would say is comfortably under 1 meter per second, and something I would feel confident describing as extreme to a group of very discerning people such as yourselves. Wobble, though, more than just giving RVs, also has the potential to separate out different components, has a lot of other things it could be applied to. So for example, here's kind of just an example of how, or like a depiction of how it works. Each panel is a different observation we have of 55 Cancri. The black dots are the data themselves. The blue is the star model for wobble, which from the definition looks exactly the same in each picture, except it's shifted by an RV shift. And then the orange is the telluric model given from wobble. And you can see how the orange model scales with the different exposures because of the different water vapor. And then green is another method for finding a telluric model, just to compare how well it's doing. And you can see the green one also varies, so it's not wobble just making things up. So the idea is we can also use this ability to model different contributions to the stellar spectrum to disentangle contributions from stellar activity, which now is one of the largest error terms in EPRV work. So stellar activity is often thought of as you look at the integrated disk of a star, and each portion of the disk has a different feature from like a spectral feature that it's contributing. But from the spots or the activity features, you get a different contribution instead. Like they may be shifted more, they may be shallower because of the different temperature in that activity area. Needless to say, there are many different ways that it would look slightly different, and it will add to an overall line shape in your final spectrum that's asymmetric or slightly different from other ones that might even look like an RV shift and will confuse any typical ways of getting RVs out into pretending that there might be a planet there when it's really just a spot rotating or something similar like that. And so the idea is, in the same way that wobble can break down this data we have into a star model and a telluric model using the differences in how stars and tellurics behave, you can similarly use wobble to separate out an additional like stellar activity model. And in that way, your star model and the shifts associated with it would have no contributions from stellar activity. And you would know it was just from the RVs of a planet shifting the spectrum back and forth. Which brings me to my final point, maybe a point like 3.5. So I'm now running what I'm calling the EXPRES Stellar Signals Project. And so this is a project where we're giving out EXPRES data to the wider community so that they can test their different methods that we're coming up with to mitigate the stellar signals that we're seeing in extracted data that are affecting the RVs. This way, everyone has a single data set on which to compare the results with and work on, and it's high fidelity next generation data, which is what everyone is moving towards with the commissioning of all these different great spectrographs that are coming online. And so initially at the end of August, we released the first star, 101501, which is a particularly active star. The idea is that this is a good chance for teams to sort out what methods they want to work on, kind of play with the data a little bit and make sure that they understand what's happening with it. And then next week, we're going to hold the first check-in where everyone's going to zoom in and we'll answer any questions that they have about the data. We have participation from, I think, 9 teams so far, which span a lot of the most popular stellar signal mitigation techniques currently. So the challenge is organized into 2 stages, the first with 101501 data. And then starting on October 31st, we'll release the other 3 data sets. And we'll hold a second check-in of how the first data set went with 101501. And it's structured in this way because, one, we want to make sure that we understand what everyone's doing with the data and everyone understands what the data is telling them. The second check-in will also let people share the ideas that they're working on and talk with each other to try and come up with improvements or any way that they could collaborate or use the results that other teams are coming up with before they have to submit their final results. And so if one of the methods being used is trained on an activity indicator and one of the teams have already found an activity indicator that works a lot better, they can combine forces and come up with a better answer by the end of the challenge. After the second check-in, though, with the release of more data, this will also make sure that the second check-in where information is shared and also the first data set doesn't have an undue impact on the results. And so the second stage will be independent. Teams will still get to benefit from the results of the first data set, but won't be misled if someone finds some results in the data set that convinces everyone else must be true or something like that. It's kind of like a validation training set sort of thing. The results from 101501 must also work for the other stars. So it'll allow us to come up with a very secure final answer of how methods are doing on EXPRES data and what types of star they work with the best. And then February of next year, we hope to submit a report that kind of summarizes what the state of the field is currently in this effort to mitigate stellar signals, what sort of types of methods are best pursuing, and whether we noticed any sort of instrumental needs such as high resolution or high signal to noise or observing cadence. That is something that future observing strategies should take into account. And so hopefully this will be something that the whole community will find use out of, both how to mitigate stellar signals and how to get the data that best serves this need. So as a final summary, we care about instrument stability, and we found that with EXPRES, the instrument stability is 3.8 centimeters per second, and other information of the instrument performance is categorized in Blackman 2012, which is this incredible paper that goes through all different aspects of EXPRES and says how well we thought they would do and how well they are doing, which luckily was usually the same answer in most of the cases. As for the data pipeline, we have a flat relative optimal extraction pipeline that's returning a single measurement precision error of 30 centimeters per second at an SNR of 250. The pipeline is described more in detail in a Petersburg 2020 paper, and a paper describing the Excalibur method is currently in review. As for the final RVs, we're regularly returning sub-meter per second precision, especially in this case of HD 3651, which is a great marker because as an extremely eccentric planet, we know that there are very unlikely to be other planets in the system. And so this is described in a Brewer 2020 paper. We also have this great high resolution spectroscopy, atmospheric spectroscopy results from Jens, also a 2020 paper, and a few more planet papers coming out in prep. So thank you all for listening, and I'd be happy to take any questions.
Thank you so much, Lily. If you have a question for the speaker, please use the raise hand feature under the participants tab. If you are not able to unmute yourself at this time, you can also put your question in the chat and the organizers will ask it for you. So, I see a question from Chad.
So can you update us on the status of the solar telescope and the solar data? How are you doing there? I mean, it seems like we have a few stars in the field that are much quieter than the sun. And so it'd be interesting to see how Excalibur does on the sun and what we can get out of that, whether we can get any traction on activity at that level.
Yeah, so the solar telescope is working pretty well. We got a few really good nights of data in August. I don't know if Joe's on the line. Joe Lama at Lowell is the one who's primarily running the solar telescope for LDT, for EXPRES, but we also made him observe this morning, so he might be sleeping. But I would say it's turning pretty good data, and Joe and our team have worked very closely to get the same extraction pipeline running on the solar data as we have locally at Yale on the rest of the data. And then we were doing so well, we're like, let's do it, let's commit, let's move the solar telescope to the top of the dome where its final resting place. And in doing so, the fiber actually broke. And so I think it'll be a few more weeks before we have a good data set of the solar telescope, the solar data. Okay. But all initial data looks pretty good and stable.
Videos off, so you couldn't see me cringe when you said the word broke.
I know.
Well, I hope that works out. That's going to be very interesting.
Mm-hmm. Yeah, I think Joe has done great work, and it's very automated, and the few nights that we do have look very promising.
Great.
All right. Are there any additional questions for Lily? Laird.
Yeah, hi, Lily. That was a great talk. I just had a sort of a really simple question about the tip tilt mirror that you have to basically stabilize the fiber image. What kind of, I looked at it, it wasn't that obvious what kind of actuator that is. How fast, is that something you guys built custom, and how fast does it actually run?
I believe it is something we built custom, and actually we can change the speed of the motors or the actuators depending on observing needs. Usually it scales with like brightness of star, for instance, and how much signal that we're getting.
Okay, and is it sort of something like at 1 hertz? I mean, it's relatively, is it taking out mainly wind buffeting and telescope tracking? Is that the major?
I think so. I think it's slightly higher than 1 hertz. I'm trying to remember the units, but since this is something I mostly deal with between the hours of like midnight and 4 in the morning, it's a bit hard to remember. But I believe it's faster than 1 hertz. Though I know that the speed itself, so in the plot, there were 3 colors that were low, and it was on like different settings of speed, basically. So I know that the speed itself actually matters very little. Our fiber is pretty small too, so it's much smaller than what you would see projected on the telescope as the star.
Okay, thanks. All right, we have a question from Stephen.
Hi, thank you. Can you actually hear me?
Yeah.
Okay, this is actually more of a response to Laird, since LDT is kind of my baby, and I helped Deborah get the necessary data for setting up the FTT. The tip tilt is a standard PI tip tilt mirror, and the custom portion is simply setting up the collimated beam to feed that and to feed the high-speed camera. The system is capable of 600 hertz with correction up to about 100 hertz.
Okay, cool. Yeah, I just didn't. I thought I saw maybe the back of a PI actuator there, but the front end is different. So
yeah, you
okay.
did. It's a really pretty. It's a nice, really very straightforward implementation of just a tip tilt correction.
Okay, all right. So it can be. So you do run it typically as fast as 100 hertz.
It certainly can. It's got the bandwidth to get up to 1 to 200. The system is capable of 600, but the telescope frequency spectrum kind of the highest peaks we found were at about 80, and then low order stuff like essentially this the secular guiding is actually handled by the telescope, not by the tip tilt. And there's enough throw on the tip tilt that we actually, back when it was discussed, we decided not to worry about having to offload accumulated offset.
Okay, cool. Thanks.
Mm-hmm.
Thanks, Stephen.
Sure.
All right. Now for something a little bit more lighthearted, we have an entomology question from Rachel Smolin in the chat, who would like to know why it's referred to as wobble instead of wobble.
To torture people, and also I think to feel a little special. So Megan Vidal and David Hogg are the primary people who work on that at the CCA, and Hogg likes to name his codes so they're easy to refer to. And he also has this mantra where he says the name should be cute, but not too cute. And so I think wobble was the effort to make it a bit cute, though I think Hogg also thinks it might have gone into the too cute regime. It really messes with you, yeah.
All right, are there any final questions? Serena, do you want to unmute, or should I just ask your question?
Yeah, because I don't have raise hand button. I was wondering how faint have you been with this for your objects?
So for EPRV work, we've gone as faint as 8th magnitude, though it was a little bit of a mistake. Though EXPRES is also a facility instrument, so other observers have used it to observe a range of objects.
Okay, thank you.
All right, Larry, did you have an additional question, or is that your hand from earlier?
Yeah, that's my. Yeah, you can ignore my hand.
All right. In that case, I would like to invite everyone to unmute and thank Lily for an excellent talk.
Thank you guys for having me. It's a great opportunity to present my work.